Okay, if you have forgotten to hand in your homework, hand in now. Now, last week what we were studying was how this electromagnetic wave, when it leaves one medium and enters another medium, behaves. We looked at the cases when both of the medium were non-conducting. We looked at the case when one of the mediums was conducting. And finally, we looked at the case when, for example, this dispersive mediums, dispersive and dissipative mediums, basically what that means is we are talking about this dielectric constant, but in our simple model of the dielectric constant, we have seen that for a complex wave, this dielectric constant is both complex and it is also frequency dependent. And we had seen that in such a case, if the dielectric constant is complex, the refractive index, what we call the refractive index, becomes a complex number. And this complex number, the imaginary part, is basically describes the absorption of energy by the medium from this dielectric. This happens, for example, in conductors, because in conductors, our electromagnetic field creates currents, which basically dissipate energy. Or it also happens in our simple case where the electrons were bound to the atoms, but nevertheless they are dissipative forces acting on the electrons, basically, because they are not conductors, but the electrons are still free to move around without leaving their atom, but they can just move around and bump other nuclei, other electrons, and transfer its energy to the other things in our system rather than transferring it back to our electric field. So in such a system, this dissipative force results in this creation of an imaginary part in the refractive index. Hence, refractive index basically measures how much of the energy is absorbed. And there is also the real part. The real part is what we call the typical refractive index, let's say. It causes the dissipation, the frequency dispersion. The shape of the wave also changes. Of course, if we are talking about the monochromatic waves, it's just a constant, a single value. But if you are talking about the superposition of more than one monochromatic wave, then each component will move at a different velocity, at a different speed. But since they move at different speeds, different superpositions, at a given time, the superposition coefficients will be different in a sense. Let's say if you just consider it as a Fourier series, that would mean the shape will change as a function of time. Well, of course, in all these problems, we assume that our medium was infinite. Now, do you have any questions about the reflection, refraction, etc.? Now, this week we will be studying what happens if the medium is not infinite, but we are just kind of guiding the electromagnetic wave in a finite volume, or a finite cross-section more than finite volume. Any questions? So let's start with waveguides. Now, if you think over it, if you consider any of our technology, like the tablets that you are writing or reading our book, well, they mainly work with, they are electronic devices where you control the electricity, but the basic idea is not to control the electrons, but rather to control the energy flow. So your wires in your electronic devices basically control the energy. And once you think of it in terms of a control of energy, one of the things that in technology we want to achieve these years is to use the light. But light is itself an energy. So if you control energy, if you control the energy stored in light, you can just make these devices. We just need the small components. So whatever we are doing with electronics, we can do with photonics, with light, using light in principle. If we can control it, we can measure it, etc. Now, one way of guiding electromagnetic waves, which is light, is what we call the waveguides. Now, what is a waveguide? In simple terms, it's just a hollow metallic conductor. So you just have most of the time, for simplicity, we will just assume it has a rectangular cross-section. This is your waveguide. Of course, we have seen that if the metal is very thin, it will not confine the electromagnetic field, but it should have some thickness, at least a couple of skin depth. So we have seen that if you send some electric field on a electromagnetic field on a conductor, it still penetrates to some extent that we call the skin depth. And if the thickness of the conductor is much thicker than the skin depth, then nothing just basically goes beyond the conductor. So these waveguides should also have some thickness, so that basically nothing leaves them. The electromagnetic wave is confined inside. Well, we will choose our coordinate axis. Let's say this is the x-axis, this is the y-axis. So along our waveguide, we have the z-axis. And we will also assume that the conductor is a perfect conductor. Well, if it's a perfect conductor, the skin depth is 0. No electromagnetic wave can penetrate our conductor. So inside the conductor, E is equal to 0, B is equal to 0. So this is the problem that we would like to solve. Is it possible to create some electromagnetic waves inside the conductor, moving in the z direction, so that once you send some energy from one opening of your waveguide, will it be able to go to the other end? So that is what we would like to study now.
Hocam bu thickness'ın olmasının sebebi neydi?
Well, you see, if it's a perfect conductor, you don't need a thickness. But if it's not a perfect conductor, there is a skin depth. So you see, if you send an electromagnetic wave, so here you have a conductor, you send some electromagnetic wave, E, B, and let's say this is the z direction. So what happens is this is z is equal to 0, z is larger than 0, z is less than 0. As a function of z, the absolute value, the magnitude of the electric field, and so the magnitude of the B field also, just behaves like this. This is z is equal to 0. Inside the conductor, it just decays. Well, it takes 1 over E, or approximately 1/3 its initial value, at a distance of delta, which is called the skin depth. So if your whole thickness is, let's say, twice delta or 3 times delta, there's no electric field reaching there. All the electric field has been absorbed by your conductor. So that's the case what we want to study. We don't want the electric field to leak out, let's say. The electric field is all confined inside. Well, for that to be confined, we just wanted some thickness. Well, for a very good conductor, that thickness is very small. I mean, a very thin sheet will also be able to prevent any electromagnetic field leaking. In the case of a perfect conductor, the skin depth is 0.
Is it important the shape of
Well, it's important in the sense that for such rectangular cross sections, we are able to solve it in class. For another shape, I mean, you can put arbitrary shapes you want. It doesn't have to be rectangular. But rectangular shapes are easy to construct for practical reasons, and they are easy to study analytically. As we will see, we will be able to solve this problem analytically. This one, and also the coaxial waveguide. 2 cylinders. An arbitrary shape, well, you need to use computers.
Hocam kondaktörün içinde neden elektromanyetik dalga istemiyor?
It's not that we don't want it. It just cannot exist. You see, the Maxwell's equations tells us that the electric field just decays. Now, in this problem, what I want the electric field to be confined in a finite volume. Because if it's not confined in this volume, So basically what I want is I want to be able to transfer energy from one place to some other place without losing it. So that's what I want. It's just like in, let's say, in these electronic devices, you try to make them smaller and smaller so that the resistance will be smaller and smaller, so they will be able to work with smaller and smaller powers. So that's why at least, for example, if you just consider the light bulbs. When I was small, we had these light bulbs that were 100 watts. Now the light bulbs in my home is just like 6 watts. All of the light bulbs in my house, if I turn them on at the same time, they won't consume as much as a single light bulb that we used to use when I was small. Small meaning your age.
But now normally the electromagnetic wave is moving from one place to the other place without losing any energy. Like for example, a normal wave that we study in our problems. So why do we need conductors to guide them? They are.
You see, okay, good question. If I shine some light from here, a laser light, it will just go straight. You see, why do we have circuits that have these rounded wiring? Maybe you want to guide it to some other place from time to time. So that is one of the reasons why, if you want to send it to some other place, not straight ahead, but curve it. I mean, these waveguides, you can just bend it if you want to wherever you want. For example, these waveguides, if I'm not wrong, they also exist in your microwave oven. Okay, there's a part which generates the microwaves, but you want to carry that microwave to the inside your oven. Yeah, you use a waveguide to guide it, to control the flow. In just shining laser light, you are right, it just goes straight, it doesn't dissipate anything, etc., just like this one, but you are not really controlling it. So we want to control. So let's look at the electric field. Well, it will be some E0. Well, you see, we want to find some solutions which are moving in the Z direction. But we don't, I mean, they're not moving in the X or the Y direction. They are only moving in the Z direction. Nevertheless, it can have some X and Y dependence. So you see, here we have the X and Y. And similarly, if you look at the B field, it will also have a similar expression. Now, the question is, do we have solutions of Maxwell's equations which have this form? I don't know what this E0 or B0 are. Maybe they are just constants independent of X or Y. Maybe they will have some particular dependence on the X and Y. Let's also look at some boundary values. What are the boundary conditions we have? So you see, eventually Maxwell's equations will tell us what the differential equations are, but to solve those differential equations, we also need some boundary conditions. So what are our boundary conditions for these functions E0 and B0? Now, for that, we have to look at the Maxwell's equation. Let's remember our Maxwell's equations. Well, we are looking in vacuum. I will just assume that inside the waveguide is empty. But it can be the air also. Air doesn't really change much the properties of vacuum. So in vacuum, what are the Maxwell's equations? Divergence of E is equal to 0. Divergence of B is equal to curl of E. Well, let me just add the charges. I will say why I'm adding the charges in a moment. Curl of E is equal to minus del B by del T, and curl of B is equal to mu times J plus mu epsilon del E by del T. These are in medium. These are valid both inside my perfect conductor and in my waveguide in the empty space. Now, why I added those rho and mu is mainly because Okay, I'm looking at the boundary conditions, so I should be able to compare what's happening inside my conductor and just outside my conductor. Well, since it's a perfect conductor, well, I cannot really prevent rho from appearing. I cannot, well, J, definitely I will have some J. In fact, J, if I write the Ohm's law, it's just sigma times E. Sigma is infinite. Well, E will be 0, but I don't really know what J will be. So nothing prevents currents and charges to accumulate or to be created on the boundary. So these two equations do not really tell me much about the possible boundary conditions because I don't know what rho is, I don't know what J is. But the other equations, this one and this one, they are independent of currents. And this just tells me that del dot B is equal to 0, means that the perpendicular component of B is continuous. Well, B is 0 inside my conductor. B perpendicular is 0 inside my conductor. So B perpendicular should also be 0 just at the boundary of the inside of my waveguide. So B perpendicular is 0 on the surface. Now, then I have this equation. Curl of E is equal to minus del B by del T. Well, this tells me that E parallel is continuous. Well, inside a perfect conductor, the electric field is 0. So on the surface, E parallel should be E 0. And these are my boundary conditions.
Dışarıda elektromanyetik dalgalar var mı peki hocam?
Well, I don't really care what's outside. What I'm looking at, is it possible to have some electromagnetic wave inside my waveguide? That is what I'm looking at.
Ya ama şimdi dışarıda varsa içeride yoksa o zaman nasıl continuous olur?
Well, you see, what I'm saying is, inside my perfect conductor, you see, at this point it is 0, just inside my conductor. Just outside the conductor on the surface, so it should also be 0, at least the parallel component of the electric field. Similarly, well, you can have some electric field over here, but the fact that it's a perfect conductor also tells me that just outside this conductor, the parallel or the perpendicular components should be 0, just outside. The continuity does not relate this point to this point. Continuity relates this point to the neighboring point.
Bir de hocam şu rho ile J hakkında neden bir şey söyleyelim?
Well, it's a perfect conductor. An infinitesimal electric field can create some current. On the surface, those currents can cause some accumulation of charges. I don't know. Sorry. What I would like to do, what I would prefer to do is just do not assume anything about rho and J. If I can solve for my electric and magnetic field without assuming anything for rho and J, then I can ask the question, what is rho, what is J on the surface?
B'nin dik bileşenin niye sıfır olduğunu anlamadım.
You see, do you agree that this equation means that the perpendicular component of B is continuous? Inside my conductor, B is 0. Because inside my conductor, we had seen how the electromagnetic field incident on a conductor behaves inside a conductor.
Ama sonuçta elektrik kalanı var ve yükler hareket
Just 1 minute, let me finish. We know how the electric field behaves inside a conductor. Do you agree? And this delta, if you look at our expression for delta, is proportional to, you see, we had seen how the electromagnetic field incident on a conductor behaves inside a conductor. And this delta, if you look at our expression for delta, is proportional to, you see, we had seen how the electromagnetic field incident on a conductor behaves inside a conductor. Do you agree? And this delta, if you look at our expression for delta, is proportional to 1 over the conductivity. So if you have a perfect conductor, that is sigma is infinite. If sigma is infinite, the skin depth just becomes 0. That, you see, this exponential has this form. E to the power minus z over delta. You see, if sigma goes to infinity, for a perfect conductor, delta becomes 0. If delta is 0, the electric field is 0. So for a perfect conductor, we don't have this tail. It just, at z is equal to 0, it is already 0. So there is no electric field inside. Well, if there is no electric field, no currents, no magnetic field inside. It can, but all the charges, well, you see, what is a perfect conductor? Well, basically, you can create whatever current you want. That is the meaning of a perfect conductor. Okay? So let's start with assuming that initially there was no magnetic field in our waveguide. That's our initial condition. And suppose you try to put some magnetic field into your waveguide. Okay, so our initial condition is 0 magnetic field inside. And then we try to put some magnetic field inside. But remember Lenz's law. It means that a changing magnetic field induces currents to oppose the change. Now, a perfect conductor will be also perfect in opposing that change. So you won't be, there will be currents, but those currents will be such that it will keep the magnetic field constant. And since we are assuming that the initial value is 0, it will stay 0. We won't have any magnetic field inside we won't be able to change the magnetic field or add a magnetic field inside our perfect conductor. And since inside the magnetic field B perp is 0, just outside on the surface of the perfect conductor, B perp is 0. Other questions? So let's see what the Maxwell's equations tells us about this. You see, these are our now we know our boundary conditions. B perp is 0 on the surface, E parallel is 0 on the surface. So those are the boundary conditions we will impose on our electric and magnetic fields. So what about these E0 and B0 fields? So I will just try to find some equations relating these E0 and B0 fields from the Maxwell's equations. And now these Maxwell's equations I will write inside my waveguide. Well, inside my waveguide I cannot have any current, I cannot have any charge, it's empty. I started with, assuming the waveguide is empty. On the conductor, I can, of course, have currents and charge density, but not inside. So, divergence of E. This is equal to 0. So what are the equations? And, okay, so before, I will also assume that this E0 has X component, Y component, and also Z component. And similarly, B0 will have an X component, a Y component, and also a Z component. You see here I'm looking for a wave traveling in the Z direction. Nevertheless, the electric and, as we will see in a moment, the electric and the magnetic fields, they can have Z components also. In the case of infinite medium, whether in vacuum or in medium, when we didn't have any boundary conditions, the electric field and the magnetic field, they had to be perpendicular to the propagation direction, but not in this case. So that's why we are allowing some possible value of E0z and B0z. Of course, it might turn out that eventually at the end of our calculation, they might turn out to be 0, but they also might not turn out to be 0. So let's see. If that is the case, then the divergence of E is equal to 0. This is nothing but derivative of E0x with respect to x plus the derivative of E0y with respect to y plus ik E0z is equal to 0. You see, E0x, E0y, and E0z, they only depend on x and y. They do not depend on z. So the z derivative only acts on the exponent, not on E0z, and when you take the derivative of the exponent, it just, with respect to z, it just brings this factor ik. So this is our one equation that E0x and E0y and E0z should satisfy. Divergence of B is equal to 0. Well, the resulting equation constraint we have for the B0 just looks almost identical. Derivative of B0x with respect to x, derivative of B0y with respect to y, and ik times the derivative of B0z with respect to, no, there's no derivative. This is equal to 0. So if the components of E0 and the components of B0 satisfy these two equations, then we satisfy two of the Maxwell's equations. Now let's look at the other ones. Curl of E should be equal to minus del B by del T, which is I omega B. You see, if you just look at the expression of B, if you take its time derivative, it just brings a factor of minus I omega. There is a minus sign over here, so it's just I omega times B. Well, this is a vector equation. This is, in fact, 3 equations. Now, let's write those 3 equations. Let's start with the x component. I omega times B0x. So this is well, in these equations, I have those e to power I k z minus omega t factors, but they are common on both sides, so I'm just canceling them. I'm not writing them out. Well, the x component of the right-hand side is I omega B0x. The x component of the curl of E. What is the x component? Do you agree? The x component is the y component of this one multiplied with the z component of this one minus the z component of this one multiplied with the y component of that one. So I omega B0x should be equal to this one. Well, the z component, that derivative, all the z dependence is e to power I k z. So instead of the z derivative, I just write I k. This is I times k. Well, let's take the y component, I omega B0y. Well, the y component is minus the x derivative of E0z plus the z derivative of E0y, E0x, sorry. Well, again, the z derivative is just ik. Now, the y component is minus x component times the z component plus the z component times the x component. And finally, the z component is the x component of the first times the y component of the second minus the y component of the first times the x component of the second. So now we have three more equations that E0x, E0y, E0z, B0x, B0y, B0z should satisfy. And then our final Maxwell's equation, curl of B is equal to mu0 epsilon 0 del E by del T, or let me write it in this form. This is time derivative is just minus I omega over C squared times E. Again, this will give me three more equations. So let's write them. Minus I omega over C squared E0x. This is equal to, well, I will just copy it almost straight away from my previous results. It's just instead of B, I will have E. Instead of E, I will write just B. Just look at those three equations we obtained previously from the curl of E. This equation, mathematically, it just looks the same, so expressions will be identical, with only this factor will be different on the left-hand side. So I will just write it away. Del is B0z by del y minus I k B0y minus I omega over C squared E0y is equal to minus del B0z by del x plus ik b0x, and finally minus I omega over C squared E0z will be equal to derivative of b0y with respect to x minus derivative of b0x with respect to y. Okay, so how many equations we have? 3 here, 3 there, that makes 6. From the divergence of E, 1 more, 7. From the divergence of B, 1 more. We have 8 equations to solve for our 6 unknowns. Well, it won't be so complicated. It will be somewhat tedious. Now let's see what we can do. Here we have terms that contain derivatives, terms that don't contain derivatives, etc. So first let's try to express everything that doesn't contain the derivative in terms of things that contain the derivatives. So we will be able to deal with the derivatives later on. So let's see. Let's look at this equation. This equation contains E0x and B0y. Well, look at the second line from the top. That contains E0x and B0y, plus terms that have the derivative. So using those two equations, we can solve for E0x and B0y in terms of the derivatives of E0z and B0z. And let's see, it is this equation and the second equation over there. Look at this equation, it has E0y and B0x. Look at the first line, it contains E0y and B0x. So using those two equations, I can also solve for E0y and B0x in terms of the derivatives of E0z and B0z again. And, well, basically that's it. Now, I will not solve them, if you don't mind. I mean, it's just two pair of algebraic equations. And it will not teach you much, those solutions, but you will get bored. So let me just look at the result from the book.
Sadece şu 6 denklem için yapacağız değil mi hocam?
Yep. I mean, well, in fact, for those 4 equations, I will determine Ex, Ey, Bx, By, E0x, E0y, B0x, and B0y. And so it just turns out that E0x is equal to I over omega over C squared minus K squared, K dEz by dx, plus omega dBz by dy. E0y is I over omega over C squared minus K squared, K times dEz by dy minus omega dBz by dx. B0x is equal to I over omega over C squared minus K squared, K times dBz by dx minus omega over C squared dEz by dy. And finally, B0y is equal to I over omega over C squared minus K squared, K del Bz by del y plus omega over C squared del Ez by del x. Well, you see, these are 118 on page 431. And we have 2 more equations. That is left. Well, you can just put, you see, look at the last equation over there, the third one. It is the derivative of E0y minus the derivative of E0z. Well, let's just see one thing. When I take the derivative of E0y with respect to del x, E0y with respect to del x, I get the derivative of Ez with respect to derivative of x and y. Second derivative with respect to x and y, here. When I look at the E0x and take its derivative with respect to y, I get the second derivative of Ez with respect to y and then x. Here I get the second derivative of Ez with respect to x and y, here y and x. But those 2 derivatives, I can change their order. So those 2 derivatives are equal to each other. When you subtract the derivative of this one, E0x, from the derivative of E0y, E0z terms, they will cancel. You only have derivatives of Bz on the right-hand side. On the left-hand side, you only have Bz anyway. So that third equation at the top of the screen just gives you a single equation in terms of for Bz and nothing else. So once you determine Bz by solving that equation, well, you can just put it over here and obtain the other components. Do you see the cancellation? Well, you see, what we should do. We had these 6 equations from the curl of E, the curl of B. And we had seen that we can use 4 of them to express E0x, E0y, B0x, and B0y in terms of E0z and B0z. Those z's are all 0z. So you see, although we started with assuming that, well, we were suspecting that maybe the z components would just be 0. Nevertheless, we added those z components. And what we had seen is that x and y components, we can write them in terms of the z components. So, okay, these are the solutions of 4 of the Maxwell's equations that we obtained from the curl of E and the curl of B. There are the remaining 2. One of them you see the third line. So here the third line relates B0z to derivatives of E0y and E0x. But we had already solved for E0y and x in terms of E0z and B0z. So what we need to do to determine, what we have to do now is just substitute these two equations into that third line above. Now, if you look at the third line, well, let me just put it down. Now, this is my E0x. So I omega B0z is equal to minus del over del y. E0x is this one. Plus del over del x. E0y is this expression. Now let's see. These are common factors. K is common. Here I get the derivative of E0z, first with respect to x and then with respect to y, with a minus sign. Here I get the same factors. Now I have the E0z, its second derivative, first with respect to y and then with respect to x. But the order of these two derivatives do not matter. So this term cancels this term. So this term cancels this one. And what we have left is I omega B0z is equal to minus I omega over c squared minus k squared, second derivative of B0z with respect to y, plus, no, again minus I omega over c squared minus k squared, second derivative of B0z with respect to x squared. We will study the solutions now. Well, let's simplify it a bit. I can cancel the I omega factors from both sides. So I have del squared B0z by del y squared plus del squared B0z by del x squared plus omega over c squared minus k squared B0z should be equal to 0. So now I have one solution. Now, B0z should be a solution of this equation. Well, hold on. Let me write the equation for E0z. Let me see. Okay, so let me write it in this form. E0z also satisfies the same equation. You see, I don't want to find the differential equation satisfied by E0x and E0y, or B0x and B0y. I don't need them. Because basically, once I determine E0z and B0z solving this differential equation, well, I know E0x, I know E0y, I know B0x, B0y in terms of them. I don't need to solve solutions for another equation for E0x or E0y. Once I find E0z and B0z, I'm done. Oh, sorry, let me write it in this form, sorry. So in the case of E0z, just put E0z over here, E0z over here, multiply this with E0z. In the case of B0z, put B0z over here, B0z over here, multiply this factor with B0z.
Electric field is in X direction. So
I don't know. I didn't make that assumption. You see, I started with this electric field. You see, this is my electric field and this is my magnetic field. I don't know. It will be a result of my computation.
So we could solve this reflection and transmission problem like that.
Well, you see, in our previous case, when we had in the x and y direction, the wave was infinite. It was not confined to a finite cross-section. The cross-section was infinite. But of course, I mean, this solution is also valid in the case of plane waves. Well, in that case, what we had is kind of interesting. You see, E0z and B0z was 0. So how does that come from these equations? Well, you see, okay, so let's look at the E0x. Now, if E0z is 0, B0z is 0, that term in parentheses is 0. Well, E0x will be 0 unless k squared is equal to omega over c squared. So if k is equal to omega over c, then I can still have a finite E0x with 0 E0z and 0 B0z. Now, then the next question, can I have both E0z and B0z equal to 0? Both of them equal to 0. Now, of course, if I want both of them to be equal to 0, also in the case of a waveguide, if I'm looking for a waveguide, in the infinite cross-section case, there's no problem. I can set E0z is equal to 0, B0z is equal to 0, and so E0x is just, let's say E0x will be non-zero only if that k minus omega over c is 0. K squared is equal to omega over c squared. That's the solution we know. But let's see, if we have a waveguide, can I still have both E0z and B0z equal to 0? And still have E0x and E0y non-zero in the case of a waveguide? Let's discuss it in a moment. Let's discuss the polarization. The polarization is just the direction of the electric field. I'm not really looking at that. The question I have is, you see, in the case of plane waves, not inside the waveguide, we had seen that if the wave is moving in the z direction, the polarization should be perpendicular to the z direction. Well, this formalism over here, up to this point, we never used the fact that we are using a waveguide. We only made the assumption that the electric field electric and magnetic fields can be written in this form. Well, for plane waves moving in the z direction, well, the same form also holds for them. It just turns out that E0 and B0, they are also constants independent of x and y. But nevertheless, the form is the same. So we should get exactly the same equations for various components of E0z and B0z, E0x and E0 and the B0. Well, we also know that B0z in that case is 0 in the case of infinite cross-section. But you see, in this case, we seem to be having this problem over here that x and y components of E0 and B0 we can write in terms of the z components of E0 and B0. So if the z components are 0, just like in the infinite plane wave, still we can have the E0x and E0y non-zero only if k is equal to omega over c. Well, that was the condition we had derived also for monochromatic plane waves. Basically, they are consistent. The frameworks that we are working on are consistent with each other. Now, my question is this one. Okay, in the case of plane waves, E0z and B0z, they are 0, and in fact, they turn out they have to be 0 in that case. Is it possible to have both of them 0 also in this case when we have a waveguide? We will see that it's not possible. Well, let's give a break now, a 10-minute break, and after the break we will see what are the solutions. We will be solving these equations in a moment. We will see explicitly what are the possible ways.
Hocam şimdi